Just checking. Sorry. Let's see. Okay, perfect. So we're here. What are we doing today? As you might already be able to tell from the title of the video, we're going to try and implement, memory to memory DMA transfer in as little lines as possible. I'm aiming for 10. We'll see if we can get it done for that. But let's do a little recap of how we got here. So I've been working on Zephyr for the last few months, and one of the things I'm kind of working on right now is making sure a lot of video cameras work with video drivers in Zephyr. And so during doing this, I ran into an issue with STM32H7, the one on the Giga Arduino, and I'm trying to interface it with OV7670 camera. And in doing that, I realized there was an issue with the DMA and the DMA marks and all of those things. And usually when I encounter problems like this, it's much simpler. It breaks the problem much simpler if I go and if I work on implementing like a simpler version of the problem before I build up into going to attack the actual problem I'm having. So with me is STM32F4, my usual development board. And what I'm going to do is I'm going to see if I can minimally get DMA to transfer a number of bytes or bits. That way I can do a memory to memory transfer using DMA, and then later on when I'm on the Arduino Giga, I can work on getting DMA working on top of or rather DMA marks working on top of DMA, because it could be the opposite. It could be DMA working on top of DMA marks, because the multiplexer actually chooses which channel and stream and such. And then on our F4, it's quite simple. We have what I think it's 8 streams, and each stream has 8 channels, and that's it. There's no maxing, there's no this or that. So this is a simpler version of the problem to implement. So I think what we're going to do today is copy between a source array and a destination array. Then after that, we're going to do some indicators so that we can kind of get a feel for what's going on. I'm going to be using CMSIS, which is the Cortex language. Really, it's just a bunch of markers that are defined that identify basically registers on Cortex processors, and that's what I'm going to be using to work with the Cortex processor on the STM32F4. So without further ado, let us begin. So the first thing we do is let's define sort of what buffer size, a buffer, okay? How many items do we want to hold and move? So let's define a scratch pad area to put that in. So define buffer size, let's say we're working with some odd thing that has 54, you can't do that in C, 54 bits, or no, 54 bytes, okay? So 54 bytes of data, you want to receive some 54 bytes, or let's even make it 24. Maybe we are sampling audio signals and we're going to be getting 24 bytes from somewhere, okay? And then let's make some array to hold, the initial bytes, and then another array for us which is going to be the source of the information, and then let's make also an array to hold the destination. So this is the container we're copying it from, and this is the container we're copying it to. So let's do that. 32 underscore 32T, and then let's say source source, what do we call it? Naming is hard. Source buffer, and then that has a buffer size, and we will not initialize it. We'll initialize it just now. You int 32t and then dest buffer. I'd like that to go like that, and then buffer. Yep. Let's use that, and then we can also initialize this to be filled with zeros. So right now we have two containers. We have one container that is going to be holding our initial amount of information, and we have another container that's going to be holding our once we copy the information from the first container to the second one. So that's going to be the second one. Let's save that as we go along. So this is just my skeleton application, and what I have in here is a little busy wait function just to cause delays so that you can visualize things in human timescales. And then I have a bunch of LEDs set up so that we can use them as indicators rather than having to jump through GDB so that we can look at what is in registers and such. Although that might be a good video to do one day. Okay, cool, because it's quite interesting. So okay, so let's start by looking at some documentation. This is kind of the procedure of setting up DMA. You can go through the whole controller's functional description and the features and such to understand it in depth. But I think today we're trying to see if we can get it done really quickly. So let's go straight to the meat. And what we find here is instructions that are needed, or rather whatever steps we need to do in order to have DMA set up and working. Okay, so let's go through the steps and try and put them in code and see what happens. So if the stream is enabled, disable it by resetting the EN bit and in the DMA stream control register, and then usually DMA doesn't go off immediately because there might be something that's going on. So what you usually need to do is after you set it off, you need to look at the status registers and make sure that either the high status register or the low status register, just depending on which channel you use. You need to look at the registers so that you can determine whether the work is done, and then you now know it's off, and then you can go on to configuring DMA. And then you need to set the peripheral port address, where this is when you're doing let's jump into that feature quickly. Memory to memory, DMA main features. I think there's a DMA transfer, DMA. Where is that? Is this here? Yeah, memory to memory mode. So in memory to the DMA can also work by being triggered by software, and in memory to memory mode you use the same registers that you would use as peripheral to memory mode. But the thing is, the peripheral one is now assumed to be the source, and that's data is copied until the counter, or rather the size. That's why we define the buffer size. So it's gonna go bit by bit until all those bits in the buffers are done. Okay, cool. So let's look at the stream configuration procedure. So the second step is going to be setting the peripheral port, which is the source of the data, so from, and then we need to set the memory port, which is the which I would call the destination of the data. So this is you need to point to some address. You need to point to address X. We will copy from address X. Point to address Y. We will copy to address Y. So it's memory to memory, from this address to that address, rather than peripheral to memory or memory to peripheral, which we can also observe later in another video. And then after you do this, you need to configure the total number of items that you're going to be sending. And then after you configure the total number of items that you're going to be sending, you need to select the DMA channel. And then after you select the channel, you need to choose a controller. So it depends on if you need a controller. In our case, because of memory to memory, we do not need a controller, and that's it defaults to the DMA controller, so we won't be needing to do this. And also, since we're using CMSIS for the definitions, for the register definitions, we will find that our streams and channels are already selected by basically how we start writing the code, and that's going to make it a little bit easier. And then we need to configure the stream priority, which is going to assist us in just if you have many, if you have many DMA operations going on, and one of them is more important than the other, so you use these priorities to choose. Otherwise, it's gonna choose. If two streams have the same priority, the stream with the lower number, if a stream 7 and a stream 0 have the same priority, stream 0 will be given priority. All of this information is in the reference module that I'm going through right now. And then, of course, you need to configure the FIFO usage. It's usually disabled, and in our case, since we're doing memory to memory, we're not allowed to do FIFO and a circular, I think, in memory to memory mode. Circular and direct modes are not allowed, and I think we can't use the FIFO register. We can only use the FIFO register or fast in, fast out registers when we are, I think, doing circular and direct modes. Maybe not even in direct mode. Okay, cool. So let's keep going. And then we need to configure the data transfer and the direction. So there's memory to memory, peripheral to memory, and memory to peripheral. So we need to choose by that. And then we need to activate the stream. And by virtue of DMA being what it is, once the stream is activated, and in our case it being memory to memory, it's going to start copying the data immediately. But usually when you're doing peripheral to memory or memory to peripheral, you'll find that the peripheral has control because it can indicate when it's ready for data or when there's data ready from it. So let's go into the code and start implementing this from the beginning, I guess. Okay, cool. So the first thing we need to do, I think, what would be prudent to do here is let's initialize our source buffer with some data so that so that we have known, you don't want to work with unknown or random data. And then, okay, I equals 0, and then I is less than buffer size, and then I plus plus, and that's that. So let's do that, and then in this for we're going to do source buffer. Alright, and then I'm gonna say I equals to I plus 2. I'm just trying to be random here. There's nothing special about these figures. It's just to make sure I don't have any basically zeros, because I initialize my destination buffer with 0, and later I will check to make sure that they're not. I'll do a sanity check later to make sure that none of them is equal to. Well, I need to make sure that something is copied over, and since the destination buffer is initialized to all zeros, if none of the source buffers is ever set to a 0 and I find a 0 in the destination buffer, I'll know something was wrong. So basically I'm making a scenario where I have known data to work with, so that when I come to check this stuff later, I can make it work. So what's the next thing we need to do? Let's consult our reference manual. So the first thing we need to do is let's disable the stream and wait for it to be disabled so that we can actually start configuring it. So let's disable it, and that's going to be like, sorry about that, RCC, let's HB1 ENR, and then let's set RCC HB1 ENR DMA2. Why did I do this? Let's quickly run to the document. So memory mode, because DMA2 is the one whose peripheral port is connected to the memories. If I remember this correctly, DMA2 is a controller that can work with memory to memory transfers. So DMA1 cannot do it. So we automatically our controller has already been chosen for us. Okay, cool. So we need to do that, and then we need let's reset now. That's been I think that's RCC. That work? Yeah. And then let's disable stream. So that's DMA2 stream 0. This is just how this is a macro defined by CMSIS for us to use when we are working with this register, basically. So what we want to do is we want to set this to 0, but then we want to wait until we get a status from the lower while. Okay, so this will be DMA2 stream 0-CR, and the control register of this stream, check the enable bit. Let's check the enable bit on DMA SX CR. Yeah. So let's check that this is not set. Basically, this is a while it's a, how would I call it? What would I term this? This is a, it will hang in the loop until this statement is true. And the statement we're checking right now is that the DMA control register's enable bit is not set. Okay, so once it is not set, we can go on. Okay, cool. So that's the first one. And then the second one is to set the peripheral address. So let's go and look at the registers. I'm beginning to forget which ones I need to use, so I need to go back and check as so we looked at the low. We looked at the configuration one. We looked at, I believe, bit 0, which is enable of, this is the stream, bit 0, enable. We waited until this was disabled, and then now we're here. So now what we want to do is set the peripheral address, which should be somewhere here, I think. Peripheral address, yeah. Peripheral address, so yeah. So base of address, so data register from to. Okay, so let's set this into source buffer. So set addresses. Okay, so DMA2 string 0, isn't it? PAR. PAR. And then here we want to int, let's cast that array into a pointer, do int 32 underscore t, and then we'll say source buffer. Okay, and then I think the next one is to set the destination, isn't it? Let's set the DMA2 string 0, and then let's do the same And then let's do unit 32 T, and then test buffer. Okay, cool. So now we've set the to peripheral address, which is where the data is coming from, and then we've set the memory address. And then let's do configure the total number of items to be sent. So I believe there's a address number of data, SN.tr. Okay, cool. SN number of data items to be sent. So let's go here and then DMA 2 to come on stream 0. So this is, what are we doing? Number of items. Okay. We'll do SN.tr and DTR. And then let's say set this one to buffer size. Okay. And then after that, let's do what? Stream configuration procedure. We've done that. Configure the total number. Let's select the channel. So I'm not going to select a channel select from the here it is. No, sorry. I'm not going to select a channel from the channel select one here, which is let's go in, it's in the control configuration here, because the default one is 0, so it will just use the 0 one. So I'm not going to choose that, just to make the code simpler, because I'm trying to get this done in as little lines as possible. And then after that, what do we need to do? Configuration. Number channel has been selected. If the peripheral is, we don't need to set anything for the flow controller, because okay, the flow controller is DMA, basically the nodes are here, and when we are using memory to memory, the DMA controller is a full controller, and we don't need to do anything about that, basically. So we don't need to do that. You probably need to use this if you're doing SDIO stuff and SD card stuff, and some peripherals. Okay, SDIO mostly. And then let's configure the stream priority. Let's see, where is stream priority in SXCR? Where is SXCR configuration? Stream priority is 1716 01 medium. Okay, let's do I think let's do a medium, something like that. Medium? Yeah, let's do a medium. Priority. So DMA 2 stream 0, and then we still want a 6CR, and then we want to set, and then let's do for x1, and then for x1, and then let's I think DMA is XCR, and then that's PL push. So let's shift that like that. Set, okay. Well, just leave a line gap. Anyways. And then after that, after setting the priority, what do we need to do? Wait. Come on, give me my mouse. Okay, cool, sorry. Stream configuration. We've set the priority. Okay. Configure FIFO usage. We're not going to be using the FIFO, so we don't need to do that. Let's configure the data transfer direction. So transfer direction is mostly in the CR. Okay, let's look configuration register. Transfer directions, probably one of the fast ones. Directions. It's probably a 1 and 2 and a 1 and a 2 or something like that. Okay, peripheral to peripheral. 0 0 0 1 memory to peripheral 1 0 to, okay, so 0 cross 2. Let's do a 0 cross 2 direction, set direction, and that's DMA 2 string 0. Let's do CR. Wait, is it CR? Is it CR? Yeah, I think it is. X2, and then let's move that to DMA as XCR, and then that's and then pause, and this is good. And then after that, let's do what? Configuration process. We've configured the direction. The direction peripheral. So we need to. We're copying 24 words. Wait, is it 24 words? How do I say this? 24 32 bit items. So each one is in a 32-bit address. So what we need to do is, once we copy one, we need to move to the next address, so that we can get all of them. Remember, the pointer gives us the first element in the array. So we want to set up those sizes so that we can actually set it to increment. So let's set p-inc and minc. So these are actually the status registers that we were talking about. So pink and mink is memory increment mode and peripheral increment mode. So it copies from the next address to the next address. So you want it to do that by itself, so that you don't actually have to DMA 2 string 0. And then here, let's do CR, and then let's set that to OX2 as well, because that was it's 1 1 0. Okay. DMA SXCR, and then pause. I think so. Actually, we can, instead of doing this, we can just set it. Can't we? Mink pause. Yeah. Sorry. Mink. Is that? Yeah, that should set it. Okay. And then the pink as well. Pink as well. CR equals DMA CR. Okay, cool. So what's the next thing to do? Let's look at the stream configuration. The next thing to do is we've done, okay, so we need to do peripheral memory and memory data widths. So we need to set the M size and P size. So let's look at these items in the configuration register, so we know what we're looking with. So M size, memory data size. Okay, so how much 32-bit we're going to be using, and P size also 32-bit we're going to be using. So I'll just do that. And okay, 32-bit is 10 and 32-bit is 10. So OX2, OX2. So let's do P size and PM size. So that's DMA2 string 0 0. Then we're going to go to the CR register, and then we're going to I think set, and then this is going to be 0 cross 2, and then this is going to be 0 cross 2, and then this is going to be what? DMA SSX CR piece size. Yeah. DMA2 stream 0, and then the control register or configuration register. Then the same thing works to, let's do that, DMA M size plus. Okay, so we've done that, we've done all of that, and then what do we need to do? Okay, so let's look at here. Procedure, we've done that, circular mode, all of that. Then we need to activate the stream. The moment we activate this stream, it's going to start working. However, that almost brings us to the first problem. We need to set up we need to enable the interrupts so that we can react to, number one, I want to be able to react to it finishing. And once it finishes, I also want to do a sanity check just to make sure the data is what it should be. Okay, so let's enable the interrupts so that we can actually get a signal when nvic enable, and then here we're going to do DMA2 string 0. So we're going to enable the request number for DMA0. So at this point, let's GPID, let's indicate that we've enabled all of this. Yes, RR, and then let's do that, and then let's enable the blue light, GPID, BSRR, bit set 15. I think that should work. And then let's do a busy wait. Busy wait. Let's do 200. And then here, let's now DMA2. The first thing you do before, look, so whenever you enable the stream, as soon as the stream is enabled, you need, before you enable this bit, so I mean, let's just go to the configuration. When you enable a stream, you need to check that all the statuses, you need to read the statuses so that the DMA, you need to read the statuses so that DMA can write to enabled. The same thing we did when we were doing the same thing we did when we were starting this. Before we started, we need to make sure there is no pending statuses and clear any pending statuses so that the machine can actually act correctly. Okay, cool. So let's actually live star and then equals DMA live CR and then CT So if you look at that, CTI4 live SR, okay, CTIF0, what I'm doing is I'm just clearing it. I'm just clearing that stream transfer clear. So I'm just making sure everything is clear, and then now let's DMA get to stream 0 CR. Let's enable DMA SX CR. Okay, cool. So that's all we need to do in our main function. However, let's remember this. We enabled some interrupts here, and this will ideally work, but then we won't know when the procedure starts, when the procedure finishes, and because of that, we won't be able to do some checks which will inform us of whether things are working right or not working right. So let's handle this interrupt, and then we can check that our code actually works. So the DMA2, I think it's void DMA2 stream handler. By the way, all of this is defined in your startup file. There's weak functions for this, so it's not that I know it, it's just that I've done it, I've repeated it a lot of times, so I'm kind of no. So okay, let's check if the transfer is complete. SR. So lower the lower status register basically, and then let's check that lower status register, and then let's check that this bit SR TCIF 0. So now these numbers are pertaining to the actual channel that we're using. If we go back, TCIF, so sorry, TCIF 0 X, you see. So LIFR, that's here, TCIF, yeah. See, so we want to uninterrupted occurs, so probably we're checking which how do I say it? Did we get a completion, and did we get a completion on this channel, if that makes any sense. So yeah, stream transfer complete on channel X. Okay, cool. So let's do some stuff in here. So first of all, in here, let's say that number one, the stream has been let us indicate to the user that the stream has been completed. So GPIO BSRR, and then let's set GPIO BSRR number 13. It's set number 13. Okay, that's cool. So that's the orange light. Let's put on the orange light to make sure to why is it here? Sorry. Orange indicator. And then let's do blue session start blue. Okay, cool. And then let's now jump into here and see if we can let's jump into here and see if we can. What I want to do in here is just make sure that DMA2, let's just make sure that the transaction is complete, and I want to live if CR and then I want to equals to DMA2. I want to clear it. Leave CR, and then let's do CTIF0. I think. Yeah. So what I'm doing there is I'm just clearing the register, and then DMA2 string 0 CR. I'm gonna disable the string equals SX DMA SXCR. Okay, let's disable the same, and then let's do a check. Check if data was copied to test. Okay, so we know it's 24 items. 24 items. We were trying to replicate some sort of audio thing. If test buffer, if test buffer, what is happening? If test buffer. So yeah, once actually, let's do this. Control SQ. Busy. Wait. Remember, these things happen in computer timescales, and you want to be able to see the gaps of the times before these actions are done. So it's good. So and then if let's now just if test buffer, right? Let's pick an item number 18 is equal to source buffer, right? Number 18. Then you have likely succeeded because it was all full of zeros, and now if it has this, it is good. We can actually make this a more comprehensive test and change everything, but let's PID BSRR, let's set GPIO D BSRR BS. Let's do 12, the green one. Green complete. Okay. Else GPID BSRR equals GPID BSRR PS. Which one's the red one? Where's my mouse? Number 14. 14. This and that. That's that. Okay. Okay, cool. I have my code here all written up. Let's see if it actually saves. Oh, I know what the problem is here. Okay, and this as well. This is not DMA2. This is not GPID. No, actually this is GPID. Come on. GPID, BSRR, why? No, come on. Bit reset, register. No, I think it's fine. Okay, cool. Let's compile this and see if it works. Oh, I see what the problem is. And then I see. This is spelling. Okay, cool. So let's see. See, this is what happens when you type code in front of people. Okay, cool. Well, I type code in front of all of you. Yeah, why is that? Why is that? Why is that? Come on, come on. Come on, come on, come on. Figure it out, figure it out. 0. Okay, cool. So that built. So let's look at it. I'm going to raise it here, and I'm hoping I can see the color of the LEDs there. Let's see. And I'm going to flash it now. Blue. Let's wait. Give it 10-15 seconds. That's kind of the delay I put in. Let's see if it goes to orange. Might be broken. And might have to go back and revisit it. So it just goes for blue and never goes past blue. Okay. Let us revisit our code. So we light up the blue LED, then we do a busy wait for 200. Then we do DMA2, DMA2 LIFCR equals DMA LIFCR CTIC F0. And then DMA, we disable that stream. Ha! I understand. Here's our problem. Hi. 0. It's always DMA2. Okay, cool. Let's do another build. Cool. Let's try. Let's try. Here's the code. I can see there. I can see the reflection. Build. Flash. Should flash now. Blue. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's not changing. Rather, it's not changing as soon as I expected it to. I might have put in too long of a delay. But in the meanwhile, let's be checking the code. I think I might have made a mistake. It's gonna be in the interrupt handler probably. Yeah. Stream 0. There you go. There you go. Cool. Like it as well. Okay, cool. Let's look at it again. Here's a video. need to reconnect my, is it reset? Outing. TDO. I think this is BB3. That should be good. That's it. Okay, let's try flash again. Goes blue. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20. Does it go green ever? Okay, cool. So let's go look again. Where did we mess up? We disable the stream. Wait, we never even cross into the orange indicator. So void DMA2 stream 0 IRQ handler. Is this how it's spelled? I'll go check the CMSIS code. DMA2 stream 0 IRQ handler. Yeah. And then IRQN, DMA2 stream 0 IRQN. I think we did the right thing. Okay, so let's revisit this. We did fill that, we did that to enable DMA, we stopped DMA, we've done all of that, we've done X1, stream 0, everything is to stream 0, yes? DMA2 stream 0, BOR, DMA2 stream 0, DMA2 stream 0, DMA2 stream 0, DMA2 stream 0. Is there anywhere we're not? M size, port size, ink, P ink, buffer size. We did not enable the interrupts. I think so. DMA2 stream 0, and then that is CR, and then DMA SX CR, TCI. Okay, cool. So let's try again. One, two, three. Okay, flashed. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 seconds. Okay. Good. So that's not working. What else did we not do? DMA2 stream 0 XTIE. Did we set the buffer size? Yes. Did we set the destination buffer, the source buffer? Yes. Did we set the direction? Yeah. Did we we set the M size? Yes. Did we set the P size? Yes. Did we set the priority? Yes. Did we set memory increment? Yeah. Yeah. Enable the interrupt? Yeah. And then we set the PAR to our source and M0AR to our destination. And what is it? The blue one. We go to a busy wait for 200, and then we do DMA 2, live CR equals DMA 2 DMA live CR CTI F0. Okay, and then we enable the DMA. Okay, let's see again. Does this end up working? Okay. Flashed. Okay. Orange. We have orange data. Green. I think I see a green. Wow. Well, let's reset that so we see if it goes slowly. Blue, orange, green. There you go. It's slow enough that I can say the words blue, orange, green. So what did we do? Let's get a recap. And anyways, as I promised in the beginning of the video, let's count the lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, yeah, 19 lines. But if you do recognize that 1, 2, 3, 4, 5, 6, 7, all the control register ones can be ORed in the same line. And basically what happens there is, how do I say this? What happens there is that they can become one line, and this simply goes back into like an 8-line function. But what did we manage to do today? So we set up the DMA controller 2, and then we set up a source buffer or a source point where we copied data from, and in this source point we put in some dummy data. Basically, we just put in some integers. What was it? 24 integers into that. And then once we do that, we set up the stream, and we set it up with its direction. We set it up to increase every time it copies 1 byte, it goes to the next byte, and so on and so forth. And we set the size of our source and the size of our destination. And then we enabled our interrupts, and then we handled the process complete interrupt. And when the process complete interrupt ran, we checked on whether the item in the destination is equal to the item in the in the source, and it was true. And you can run a comprehensive test before and after just to know that actually your data was copied over, and I think this is it. So that's been cool. It's taken us an hour to write around 20 lines of code just to know how long it takes, and we've had to refer to several documents. We've had to drop into actual libraries code to check whether we were using the correct macros, and in some cases we were using the wrong ones. And even when the code compiled and ran very well, it was still wrong in some respects, but we've managed to fix it in the end. Thank you. That was memory to memory DMA in less than 10 lines, and I'll see you next time. I'll see what we do. Thank you so much. Cheers. Come on, stop the stream. They're still here. Why?